Okay, ready to go. So apologize. Hopefully this is the last travel of the year. We don't have that much left, but I don't have anything else planned. So today our topic is context switch. So essentially, I kind of say that context switch is arguably one of the most interesting lectures because it kind of tells you what happens and how you switch between processes and threads of execution, right? And just to remind everyone where we are, so last time we talked about user init, so specifically this function, which we were calling from main, right? So essentially, and this is how the whole class started. So we booted into main, right? So then we initialized memory allocator with this kernel init1, allocating all the memory from the end symbol until the 4th megabyte. We created a new kernel page table. We initialized the global descriptor table, initialized the interrupt descriptor table, global descriptor table. And we skipped a little bit here. So there are some functions here which like they're more low level. They initialize interrupt controllers and stuff like that. And eventually, but it's still kind of like instruction pointer of the CPU was always incrementing, right? And so last time we reached this user init, and this user init, what it did is that it created the very first process in the system, right? And more specifically, just that init process, what it literally did, it was a piece of assembly code, but it executed the exact system call with the path of init. And init is a process written in C. So this is the source code, roughly speaking. So it starts with main and everything else, and then it goes into the infinite loop, and it prints on a screen that init has started, right? And what it means is that at this point, you're ready to run, to boot into the shell. In order to boot into the shell, init says, okay, I will fork myself, so I will execute fork. And like if something goes wrong, then the fork failed and we exiting. That's kind of bad because I'm not sure that x86 can handle the this error, and what happens next, I don't remember. But if everything is okay, it forked, it's inside the child here. It says, okay, I will replace my child with this shell, and it execs into a shell. Again, exec can fail. Hopefully it doesn't happen. And typically, this is it. So at this point, you have two processes, right, in a system. You have init and fork, and both of them are running concurrently. So, and the operating system will be context switching between them. And that's why in x86, if you try to exit from a shell, nothing really, it seems like nothing happens, right? Because it gets another iteration of this loop. It gets back to this for loop, forks again, starts a new shell. In an x86, essentially, despite the fact that you can technically exit from a shell, doesn't buy you much because you immediately get into another shell, right? So just wanted to understand, to make sure that we understand how everything boots, right? So essentially, just connect my Wacom tablet here. So essentially, we keep returning to the shell, and the init process supposedly will be running forever, unless like we run out of memory and exec or fork fail, right? Which can happen, but never happens in practice, in our case at least. Okay, we got it. So we say, okay, sure, that's fine. But really, how do we really start running even the init process, right? And then later shell. By the end of the main function, what happens here is the following. So the very last function in main is this MP main. MP main function is actually executed on every CPU of the system, right? So we will talk later on, we talk about how the x86 detects other physical CPU, how it initializes them, but essentially only one CPU will execute the full main because other CPUs don't need to go through the all steps of initialization, really like some simpler sequence is sufficient, right? But all of them will be finishing with this MP main function. And this MP main function, as I was kind of saying last time, what it is doing is the following. So it says, okay, look, I will print this line saying that CPU number 0, 1, 2, 3 is starting, and it does bits of CPU specific initialization. This loads the interrupt descriptor table with the instance of the interrupt descriptor table register with the instance of the interrupt descriptor table. And then eventually it goes into this scheduler, right? And this scheduler is an infinite loop, which never exits. And specifically within this first function, like x86 will maintain a list of processes. And this list of processes essentially, let me just power here. So it's connected. This one is still has power. Cool. Yeah, this one will connect now. So essentially, x86 will have a list of processes like P1, P2, P3, and so on. Right now, there are only two. There is init. Like initially, there is just simply init because init hasn't even forked yet. And so this function scheduler will switch into P1. This P1 will go back into the kernel, execute, as we saw it execute fork. The fork will create this P2. P2 executes exec and becomes a shell. And essentially for a while, until you type something, x86 will have only two processes. And essentially, every time the timer interrupt comes in, x86 will be implementing the logic of switching between P1 back to P2, from P2 back to P1, right? And this is the topic of our lecture, essentially, how this switch happens. So essentially, our goal is to understand how this is implemented, because it looks a little magical, because, right, my whole point that if you have a CPU, it executes just fetch, decode, and execute. Roughly speaking, I'm like severely simplifying the logic of the pipelines and out of order CPUs, but roughly speaking, the instruction pointer just rolls forward, right? And up until now, it kind of was rolling forward, right? So nothing was happening. But in the end, the way we see the operating system on the screen, we see it as a collection of like interactive windows, right? Whatever is happening, some word processors, whatnot. And all of these are essentially processes, P1, P2, P3. And it's just that the system operating system like switches between them so fast that we cannot even notice, right? And the logic of this switch, like from one process to another, is the topic of today's lecture. So let me quickly change to the to a new slide deck, because we were finishing, right? I think we just finished the last lecture, and let me quickly start the context switch lecture. Just switch to it. Slideshow. Okay, so context switch. So again, so we kind of understand, right? So we just talked about it. We get the point that operating system, again, so CPU is kind of flat. That's the main point which I'm trying to explain. It executes instruction one at a time, right? And then occasionally it says, okay, I gotta switch and start executing some other instructions, right? And those instructions, we might see something like a shell on a screen. Then a timer interrupt comes in. We switch maybe back to scheduler. This schedule function in x86. It picks the next process. So it essentially says, okay, I get it. I have a list of processes. I will pick the next one to run, and I will switch to that other one. And maybe that other one was, I don't know, maybe it was init. And init doesn't have to do much, but it's still running, right? And again, the timer interrupt comes, or maybe some other condition. Maybe init goes into the kernel and it has to wait, and it voluntarily gives up the CPU. And again, a little bit of a scheduler runs here, and then back again switches to yet another process, right? And essentially, it's kind of like everything is everything is sequential, right? So you're still executing the CPU. This is just one instruction here, which kind of like does the switch and continues executing. But nevertheless, if you switch fast enough, you just a human thinks that okay, like a bunch of things are running, right? So this idea is clear. Let me stop here for questions, if there are any. Okay, probably it's not that hard. So okay, uh, let me ask you a question. So when do you think we switch between processes? If you were a designer of an operating system, in what cases you might decide to switch to a different process and stop running one, switch to another?
Whenever one's process starts doing a system call, possibly, or an
Possibly.
interrupt.
What is your logic here? So imagine you do something like a exec system call, which we covered last time, right? Um, Internally, you do int 64, get into the kernel, and we saw the logic of exec, right? So we saw each instruction of exec, right? And at some point, exec says, okay, I will replace the address space of this process. So kind of it's just to be specific, it's the same process data structure proc, if I remember correctly, and it was pointing to one page table. We created another one, then we switched the page table. But it looked to me that after that, we actually kind of like exited back into that process. So no context switch happened, right? And it's kind of logical. You say, look, it's kind of like calling a function of a library. So you don't really have to switch here. So not all system calls will switch, but which ones? You also mentioned an interrupt, and I keep mentioning a timer interrupt. So obviously, one reason is the timer interrupt, and a timer interrupt is configured by the operating system. It says, okay, please interrupt me. Let's say every 100 nanoseconds, milliseconds. Uh, and sometimes say if it's too long for a human, maybe every 10 nanoseconds, right? And 10 nanoseconds, I mean, I don't know why I'm saying nanoseconds, milliseconds. 10 milliseconds is 20, like at a 2 gigahertz frequency of a CPU, it's 20 million instructions, if I'm counting correctly. So it's kind of a long chunk, right? So of course, especially for our tiny programs, which something like cat will be able to do whatever, a million iterations of a read from a standard input to standard output iterations, right? So it's a sizable period of time. Of course, if you're running Quake or something, then maybe it's a little like, I don't know how many. It gets a little tough, but still. But I just wanted to make sure that we understand that it's quite a bit of time. So yes, sure, we're gonna context switch on a timer, but I also wanted to make sure that we understand that not all system calls will switch. Which system calls will yield the CPU? What do you think?
Timers and possibly signals.
Which one? Signal and what is the other?
Timer.
Well, timer, like in xv6, if you more carefully look at the list of the system calls, it has a sleep system call, which says, okay, I want to sleep for like 1 second, for example. And yes, obviously, at this point, you go into the kernel, you change the process data structure, saying that I want to sleep. And at this point, obviously, you have two options. You can either busy wait here, doing nothing for a second, right? And that's one way to do it, because if this interval which the process want to sleep for is so short that it's shorter than the time required to implement a context switch, let's say it wants to sleep for like 100 nanoseconds, and 100 nanoseconds, as I just explained, it's only 200 cycles. It's a little rough, so we'll not be able to context switch it in under 200 cycles. So at this point, an operating system might choose to just busy wait and return. But if the process says, I want to sleep for a second, and it's, wow, how many? It's 200. No, it's 2 billion instructions, right? If I'm counting correctly again. 2 billion instructions. That's a huge interval, right? It doesn't make sense to just busy wait. And at this point, it makes sense. There is a canonical name for this. It's called yield. It makes sense to yield the CPU to another process to essentially say, look, at this point, we go into the scheduler, we'll do a switch, and we'll choose a different process to run, right? And then later on, when the timer interrupt will be coming many, many times, because if we're interrupted every 100 nanoseconds, then we will see at least 10 of those timer interrupts. I apologize, not 100 nanoseconds, 100 milliseconds. Then we'll see 10 of those timer interrupts. And on a 10th one, this process will be ready to run, and then we will switch back to this process, right? Or at least we will put it into the ready queue. And the next time it gets a chance to run, it will run, right? So system calls, which either explicitly say, I want to wait for something. There's actually an explicit yield system call because the user level says, maybe I don't have to do anything. I kind of know that the user will be waiting for something, and I explicitly yield the CPU. So there is an explicit yield system call. But also there are system calls like read and write. So for example, read, which touches the actual physical disk. And in order to read something from a disk, you need something like 10 milliseconds. Again, in my calculation, it's 20 million cycles. So it doesn't make sense to just busy wait for the result of this read system call to come back over the PCI bus from the hard drive, right? So at this point, the operating system will issue the request to the hard drive and switch to another process, and then we'll come back to this process later when the request is available, right? So things which touch IO or input-output, they usually switch because it just doesn't make sense to wait for this slow devices. And instead, operating systems implement some asynchronous processing model. I mean, in the past, when we were booting, we saw that read just simply busy waits, right? Because it was simple. We're just booting. There is nothing else to do. At this point, we can just busy wait for the disk to get ready, like be ready with the request. But real operating systems, including x86, will context switch on a slow IO operation, right? Or for example, like maybe read is trying to read even from like standard descriptor 0, something like connected to a keyboard or something like that, and it will be waiting for this input, right? So it's again a context switch, and then later on it will be woken up by a timer or a keyboard interrupt, right? Make sense? Any questions about this?
So basically, whenever we need to access a device and that access is expensive, we context switch to do something else while we're accessing.
Correct. And you have to judge how long it takes you to implement a context switch. And roughly speaking, it's in a simple operating system like x86, it may be between this is a kind of a tough bound, but you can if you're really careful, you can context switch in 1,000 cycles. In Linux, I would say it's at least 10,000 cycles or even more, because Linux does a lot of bookkeeping and stuff. So any device which will take you longer than 10,000 cycles, which is like 5,000 nanoseconds, is probably a good candidate for context switching. And again, it gets towards like a clever design and optimization, but as a general rule of thumb, yes, you will context switch instead of just busy waiting. Make sense? But again, just to remember, roughly speaking, the main reason to context switch is to pretend that we can run multiple processes at the same time. So implement this time sharing of the CPU, right? The one which I was describing here. So essentially, for a human, because this period of time is 10 milliseconds or 100 milliseconds, well, the human almost doesn't notice, right? So it's so fast that you can just like perceive those two as moving forward almost at the same time, right? And of course, it wasn't like that all the time, right? So the first machines were batch processing machines, right? So essentially, you load one big program in a mainframe into a mainframe machine, and it runs to completion. Like maybe it was computing some numbers, and it just outputs the numbers, and then you take next process from a queue and run it to completion. And it's like you say, wow, why are you even mentioning that? That's prehistoric. We don't really care. It still kind of happens today a little bit. So original GPUs, like GPUs 10 years ago, were kind of batch processing things, right? You take one kernel, runs to completion. Now they have support for context switching. Modern upcoming quantum computers are still batch machines. Like it's a quantum computer. You load the whole program and it runs till completion. And they still are figuring out how to implement time sharing and spatial sharing of those machines, right? So it's not trivial. So they're kind of like close to batch. But commodity CPUs implement this idea that you can always context switch and implement time sharing. And this way, I think this way you can get more out of this machine because you can like simply say, look, I run multiple things and it looks like if one of them has to like do an IO, then I will just wait for it to finish and do something else meanwhile. Okay, a couple of questions here. One process writes gun fishing and another process takes over until that process gets back. Kind of correct, yeah. So it's like yield is a gun fishing in our example. How does the OS know how long to wait until going back to the process that calls sleep? Does the process call sleep one pass one as an argument with yield? Kind of. So like you pass a number saying I want to sleep for a specific number of time units. And operating systems support different granularity of these units. So I think Linux will support actually nanoseconds. And if you sleep for nanoseconds, you don't even do the system call. I think you just will be busy waiting in a libc library saying that, okay, for this short period of time, we know that we're not going to even do the system call. We'll just busy wait and return immediately. However, if the period of time is something like longer than a context switch, let's say 20 milliseconds, then you go into the kernel, we'll see it later. The kernel adds you to a queue of sleeping processes. And then every timer interrupt, it will be checking whether anyone in this queue is ready. And in a simple operating system, it can just be a single linked list, and you go through the list and check who is ready. In a more complicated system, you will organize it in a sorted tree, make sure that you don't have O(n) complexity, right? And you check just the first element. If it's not ready, then no one else is ready, stuff like that, right? But essentially, every time you process a timer interrupt, I'll show you in a second, you will be checking if any process is ready to wake up. But of course, we will take a look later. It's not guaranteed that the process which are woken up is getting a chance to run right away, because maybe some higher priority processes or processes which didn't run for or had less smaller share of a CPU didn't have a chance to run, and the operating system will make a decision, like a scheduling decision, who is next. So it's not guaranteed, but at least you will be sleeping for that period of time, but maybe for longer, or at least you will not get a chance to run right away. Any other questions?
Yeah, I have a question. If the timer interrupts are like frequent, can't the time to like search through that linked list data structure take up all that time between the
Correct.
timer interrupts?
Correct. And so that's why modern operating systems pick a timer interrupt interval from, I would say, from 10 milliseconds to 100. So 100 is typical for a server. 10 is for interactive user environment, just to make sure that human is not annoyed, because we kind of can perceive intervals of 30 milliseconds, right? And as I was saying earlier, 10 milliseconds is 20 million cycles, right? So it's quite a sizable chunk of time. So yes, some fraction of it you will spend going through the tree, through the like searching who's running next, but majority of the time you will be like literally like doing some useful work. However, going much lower, so kind of like maybe 1 millisecond, like 2 million cycles, it still makes sense if you have some specific requirements why you have to respond that fast. Maybe you're doing some real-time systems and stuff. You really have to steer a wheel of your car, and if you don't process this like every 1 millisecond, then everything goes south. That happens. Yeah, it's a design decision. You're right. So you cannot put this interval you cannot make it that small. After that, you just literally processing waste all your time processing the timer interrupts, and you need to know how long it takes to process a timer interrupt. But in x86, I would say, again, it's roughly maybe 1,000 cycles. So you really can go like with a very frequent interrupts in x86. And in Linux, I would say maybe 10,000 cycles to process an interrupt. But still, yeah, you have to make this decision more careful. Like you have to be careful. But typically you don't need to. I mean, really, if you drive a car and it's a real-time task, you really have to read all the sensors, make sure that there is no collision or it's not too late to make a decision. I'm not an expert, so I don't really know how they structure those systems, but yeah, they usually run less stuff. Everything is so tightly controlled that you know that a steering process will get a chance to run every millisecond, no matter what. And the system is organized in such a manner that it will never schedule a process which will like interfere with the steering process. But I don't want to go into those details, but it can happen. Any other questions? Check the time here real quick. Okay, so let's keep going. So now let's take a look at how we can implement this context switch. So what do I have here? I have some, like, I just essentially like the same kind of reasons. Timer interrupts, process enters the kernel, and system call has to wait for some resource, kind of like IO. For example, you write to a pipe, but pipe is either full, or you read from a pipe and pipe is empty. Then you will just essentially go to like your context switch because there's literally nothing else to do. So you're going to be waiting on a pipe. In this case, pipe is kind of like a disk. You're waiting for an IO from another process. And you can just yield voluntarily when a process doesn't have anything to do. Okay, so let's concentrate on another cases are kind of similar when a timer interrupt comes, right? So we looked at it many times and literally remember how it works. It's vector 32, all traps, we save all the state, we already know what it is, then we reach the trap function, we pass the trap frame as an argument. So remember, the trap frame is essentially, it sits on a kernel stack. So this is the trap frame. This is a kernel stack of this process. Remember, we now know that the process data structure proc has a pointer to the kernel stack, and the trap frame, which we passed as an argument, just points to the same stack, and all the registers here are safe in this trap frame. And again, remember, we push the interrupt number on the stack. We know this interrupt number is the trap number, and we say, okay, if it's a timer in x86 is 32, then sure, we say we increment a number of ticks, meaning the system maintains how many times it was interrupted. This is the logic of this wake up processes, like processes which are sleeping on ticks. In x86, the granularity of a sleep is essentially one timer interrupt. So probably 10 milliseconds or 100 milliseconds. I think that's essentially you wake up everyone who is sleeping. We'll look at it later. But after that, essentially what we're doing here is this logic. We say, okay, if there is a current process, the system actually has a current process, and this process is in the running state, meaning that it was actually running when the timer interrupt arrived, because maybe there is a case that the process wasn't running, right? And the time, it's really a timer interrupt, so that the interrupt number is a timer. We're going to yield. We're going to force this process to yield, essentially preempting it and triggering a context switch into another process, right? But you got the point. So we were in user level doing some whatever, like shell was processing some commands or whatnot. A timer interrupt initiated by hardware, right? So it's like the hardware is configured to signal to the CPU every so often to raise the interrupt, forced us into the kernel. Like we reach the trap function, and we're inside the trap function invoking yield. And what I'm saying is that we're going to switch. So we have a notion of a current process, this proc here. We maintain this field. Of course, this process has an address space, everything, right? So this is the currently running process. And what I'm saying is inside this function yield, which we invoke, we will eventually reach the scheduler. and we pick another process in a list of processes. It, like in x86, it's a round robin policy, so it's very simple. You always pick the next in the list, right? But we'll take a look later. And essentially, yield will return into that other process, right? So if this one was process P1 and this is process, like CPU kept incrementing the counter, but at some point, there was an instruction pointer, EAP pointing somewhere here, and we will switch it inside these functions. Like specifically, the function will be called switch. That's how they spell it without I. And this instruction pointer will be switched to a context of another process, and this process will start returning. We'll do IRED, restore the user registers into the user level, EAP, and we'll continue running whatever, executing the logic of this second process, right? That's the high-level overview of the switch. That's what's coming, right? Make sense? Any questions about it? And we right now looking like at the point where the timer interrupt preempted us. Let me switch the color real quick. So essentially it's like this line, and we started like flowing here, right? And we will talk about this part and how we exit into this process, right? Make sense? At a high level, like, okay, sure, doesn't look that complicated. Devil is in the details a little bit, so it's kind of like surprises you a couple of times. So inside this yield function, we're going to acquire a couple of logs. We say this process, it was in a running state. We're going to leave it in a runnable state, meaning that if there are no other processes in the system in a runnable state, we will context switch back to this process or will not perform a context switch at all. We will just return to this process because maybe it's a single process in the system and nothing else is ready to run, right? But we don't know yet, so we go inside its get function. So it's invoked from yield. Inside this get function, this function switch will be responsible for switching from one process to another. It's a little magical, so we're going to take a look at how it can be done in a second. But at a high level, you got the point, right? So we just enter the kernel with a timer interrupt. We're trying to save all the state of the process, of the current process, and we'll start restoring. We'll switch here inside the switch function, and we'll start restoring the state of another process, right? Make sense? Now let me ask you a question. So what do you think should happen inside the switch function? How to implement the context switch? Do we have an idea?
Maybe change the segment descriptors so that it points to different, I don't know, to different parts of a stack or something.
In a way, but maybe anyone else has a better idea. We will change this, like some segment descriptors, switching from one process to another, but maybe you guys can someone suggest like a more concrete plan, or what needs to happen? Again, surprisingly, it's not that hard, especially if you will be looking back at it. You will say, yeah, it's totally like super duper easy, but it's a little hard to guess. But still, maybe let's think for a second. Maybe someone will have an idea. Let's think of like I have these boxes. I have an analogy of a box, which may or may not be a good analogy, but I kind of say that we have to pack all the state of a process in a box. And then if we switch from one, like imagine like you had a process which was running clock number one, and you packed everything, and then you somehow atomically with a single or a couple of instructions, you implement this switch. And if this other process has everything packed, but you have a logic how to unpack it, meaning that you like you restore all the registers, and at some point you will exit into the user level. It seems conceptually seems easy, but those boxes may not like. I ask the question, what should be in this box? But let me just draw a diagram. I think it explains. You can talk a lot about it, but it doesn't like. It's a lot easier to just like pretend that to explain it through example. So, okay, analogy with the boxes, it's clean, right? So kind of like it makes sense. So if you pack everything and you just like within one instruction, like roughly speaking, you can think of it as a pointer. There will be a pointer, some kind of a state, some kind of a pointer P. You switch it from one process to another. And if you were executing the logic of packing, which was saving the state of this process, you did a switch of a pointer, then you start executing the logic of unpacking. The dog is unhappy. She wants to build a context switch. Unpacking, and then essentially like if this is the switch function, meaning that you kind of packed everything, switch a pointer to another process, unpacked, you enter this function kind of executing process P1, but you exiting this function executing process P2, right? Kind of makes sense. In like, you can think of it as, okay, sure, what if like it's kind of, what if it's not about the processes, but about something else? Like maybe you were computing a function F and you have a list of functions and you say, look, I'm done computing F1 and I switch to F2, and you just maintain them as a list of functions. Similarly here, you can maintain everything as a list of processes, right? So roughly speaking, it makes more sense. And if we kind of look into, if I ask you a question, what is that we need to pack? Like when we talk about a process, what represents the state of a process? What is that we need to save into this box to make sure that, we can come back to it an hour later and unpack, and it will continue running? So how would one build this? Like, again, so nothing has to be very mysterious here, because if I say, look, guys, this is the process data structure on a screen, right? The process data structure represents a process. So majority of the process state is kind of already saved, because if you think of it, of this process data structure as a box, roughly speaking, it already has a pointer to its page table. It has a pointer to a kernel stack. It has a pointer to, let's say, its file descriptor table, or it has a file descriptor table as a field. It has a pointer to the current directory, has a array which represents its name. And despite the fact that the page table can change because the process can grow its address space, it's already kind of saved, because if you have this proc data structure and it has a pointer, this one page dir has a pointer to the page table, right? You already have all the, if you did like some additional like SBRK, so you grew the address space by a page or two, those changes will already be reflected in the page table, right? So you don't really need to do any specific save on this, right? So it's already remembered by the fact that you already like update this process data structure. And so if you have kind of like a list of processes, P1, then you have P2 in a system, and you have whatever number of the processes you have, you roughly speaking can say, look, I can move from process P1 to P2, and most of the state is already saved because it's like reachable from the process data structure. Make sense? So most of the state is already there. Let me see a question here. Trap frame and page directory, someone suggests. Let's get, yeah, you're actually right, trap frame. So if I ask you now a question, like we looked at this process data structure, right? So we understand that most of the state is saved. I will ask again, what is unsaved? What do we need to save? In order to come back to this process. Any ideas?
The registers?
The registers, you're right, but which registers?
Poly saved registers? Or
No, you're right. So Coley saved registers. Actually, that's the right answer. Coley saved registers. But let's for everyone, just let's make sure that we understand how it works. My next slide is registers. But I wanted to go back to this function. So just for a second. Remember this, we got to this function from this trap function. We entered the scat function. From the scat function, we enter the switch function, right? And I kind of claim that the switch function will actually do the context switch. Right now we have a proc, and this proc is a global variable. Every time we switch, we update it to point to the process data structure, which represents the current process, right? So from this current process, we will have a pointer to the page table of this process and everything, right? There are multiple ways to implement the context switch. In x6 actually switches from one process, not directly to another process. It actually switches back to the scheduler, which is a little unusual because you think, okay, why would you do this? But that's one way to do it. And essentially the switch function switches from a process to the scheduler. If I ask you a question, what is the scheduler? The answer is that, remember that infinite loop, which we actually entered from the main function at the very end of the boot. Like the scheduler is just the infinite loop. And the scheduler itself will pick a next process to run in this infinite loop. So it will access the list of processes in the system, pick the next one, and will switch to this new process, proc2, right? So if this one proc1, makes sense. So a little awkward because one would say, why can't you just pick the next process, picks next to run here, and just switch directly from process 1 to process 2? And I agree, that would be cleaner. And in fact, a couple of years ago, I was asking as an extra credit exercise to implement this logic in x6, right? And it's doable, so it's not super hard. But, and I don't really know the reason why they build this way, that when they switch from a process to a scheduler, from a scheduler to another process, but maybe this is how it was built in this original Unix version 5, which they are following, re-implementing it for modern x86 machines. But okay, sure, they made this design choice. It's a little obscure, but fine. But you got the point. So we switch in x6, we switch from a process to a scheduler, from a scheduler to a process, back to a scheduler, back to a process, and so on, right? Now the question. Imagine we were running in process P1, and I was asking a question, what is it we need to save? At some point, imagine some point later in time, we want to switch back to this process P1. Logically, we kind of say, okay, it makes sense to come back and start executing, like, of course, there will be a line within switch from which we exactly context switch. But roughly speaking, we want to come back here, right? Like we want to remember that we were executing this cat function, and we want to come back here. And if we start exiting from this cat function back, we will exit from a timer interrupt, which preempted us, right? And return to user level because we saved everything in a timer interrupt. We saved everything on a kernel stack. And we say, look, guys, if we do IRAD, then we will go back to user level and we'll continue running process P1. Does it make sense? So roughly speaking, if we can come back here, we will be okay coming back to process P1. Does everyone agree with this, or is it too complicated? Let me remind you how we got here. So we said, look, we were in a timer interrupt, like vector 32, then all traps, Vector 32 preempted execution of a user at some kind of point in user level in the text section of user code. Then we went through this trap function. Then we entered this yield function. From this yield function, we went to this get function, and we are currently in the switch function. At this point, as I was saying, the process data structure kind of remembers most of the state of the process. And the only last thing which we are missing is to how to come back to this, or like essentially, it's, again, I agree, the question is a little metaphysical, right? So the question is, what is unsafe at this point of execution? And someone said registers, or specifically call state registers, right? Because, like, let's explore this idea. Because when we started executing in a kernel, we have a kernel stack. On a kernel stack, the hardware saved the instruction pointer, code segment, stack pointer, stack segment, E flags. We pushed the trap number. We pushed all registers. We pushed segment registers. We pushed the segment registers. We entered the trap function, right? So we had the trap frame. Jesus, okay. Let it all go. Guys, for this. Then we, like, essentially we were invoking those different functions. Maybe we'll push some additional registers here, like kernel level EAX, maybe ECX. So essentially caller saved registers. And at this point, we are like about to call this switch function. And at this point, the thing which you mentioned, which registers are unsaved, if we enter the switch function internally inside the switch function, it takes 2 arguments. So we will push these 2 arguments on a stack. I kind of claim that the only registers which are still unsaved are the callee saved registers. Callee saved registers inside the switch function. Do you agree with that? Because everything else is saved. And if you save this callee saved registers in some kind of a data structure, which is reachable from a process, then if you restore this callee saved registers, and specifically instruction pointer as well, you will be able to come back to the point inside the switch function where you switch from one process to another. Does it make sense? Let me stop for questions here. So I agree, it's kind of hard to understand from the first time. So now I will go like step by step how everything gets saved, but at a high level overview, it should be kind of at least making sense. Most of the stuff is already saved because we saved the user registers when we were entering into the interrupt. We saved all the registers here. As we were moving through the kernel, we always save the caller saved registers because the kernel follows generated by the compiler. Compiler follows the calling convention. So when we enter the switch function, which we will write in assembly, we know that all the caller saved registers are already saved. And we only have to save a subset of registers, which a callee saved. And if we save them manually, then everything is saved at this point. Make sense?
Yes.
Any questions? So again, back to my analogy of the box, which may or may not be annoying. I don't know how useful it is. So let me clear everything. I keep coming back. So essentially this box contains everything about the process when we enter the switch function with 2 arguments. And only the callee saved registers are outside of this box. And inside the switch function, we will implement it in assembly. We'll carefully save those registers. So we will push every callee saved registers in a box. And after that, with a single instruction, like kind of a move instruction, we'll switch a pointer from one box to another. Since this box was prepared according to the same layout previously by a previous timer interrupt, after this move instruction, we can start unpacking. We say, okay, we know where in the box, and specifically one of these registers is an instruction pointer. So we will unpack the instruction pointer, meaning that we start executing, like it will be inside the switch function, although technically speaking, it doesn't have to be the same function. It just has to be an unpacking function. This unpacking function will restore the Coley saved registers. Right? And like if we remember the return address, we will return from this switch function to the function which called us. We'll keep returning because if we remember the stack, because from the process, right, from the process, there's a pointer to the kernel stack. On this kernel stack, there will be a return address. And similar for this process, there will be a return address which we pushed when we were like schedule called switch. I forgot exactly, yield called schedule, trap called yield, and so on, right? So all of these functions are, all of these return addresses are on the stack, on the kernel stack. You keep returning, and eventually you will reach a pointer when it's just the, like you restore everything from the trap frame, and eventually you do the IRAT function, which restores this 5 things saved by the hardware, essentially instruction, user instruction pointer, EAP, user code segment, user stack segments, and E-flags. And since you're restoring the code segment, remember we jump back to the, if the interrupt preempted us from the user level, we will go back to the user level, privilege level 3, and we'll continue running in user level. Make sense? So this is kind of the most important part here, is to understand this idea that, you know, the only things which are, when we enter the switch function, this box contains almost everything. We only have to save Coley saved registers and instruction pointer. And then we, with a single instruction, we move from one process to another and then start unpacking the other into the registers and then exit back into the user level. Let me stop here for questions. So I have a couple in chat. So all general purpose registers are saved twice, once in trap frame and once in switch. That's a good question. So actually, in a way, how to answer it better? Where's my, do I have a picture of a, like I had a picture of a trap frame here. So probably the best way to understand context switch is to think about the interrupts, right? The interrupt saves those registers and then restores them back when we go back to user level, right? Very carefully. So in a way, obviously, the instruction pointer is saved here once by the hardware, but then it also saved every time we, in a way, every time we call a function, we save the return address on the stack, right? So it may be saved multiple times. For example, AAX register will be saved by this, when we say save all user registers, we save them with save all instruction, right? So it's saved once here, but every time you call a function, says EAX is a caller saved register, right? So the caller will overwrite it. It will be saved on a stack again and again and again. So in some way, it's saved multiple times, right? Some registers will be saved only once, like this code segment will be saved only by the hardware when we enter the interrupt, and we never save it again, right? So let's say at least it's saved typically more than once, but you have to understand how the execution is flowing. So meaning that every time you call a function, you save some subset of registers, specifically caller saved registers, right? So because you want to come back to a function and you want to restore these registers, right? So they are saved multiple times. I don't know if it helps to answer the question because it's kind of like, it's a little weird, but I hope it at least clears the understanding. Someone sent a link to a switch function, maybe just to locate it, but we're going to talk about it in a second. Should it not return to a scheduler after process 2 returns? Should it? It does return to a scheduler. So the process 2, we'll take a look in a second, but this process 2 will, you're right, so it will go back to the scheduler. The scheduler will take a look at the list of runnable processes. And if P1 is in front of that list, it will context switch back to P1. So in case of 3 processes in a system, and all of them are runnable because they were preempted by the timer interrupt, they are not waiting on IO from disk. Because if you're waiting from IO, then the process will be not in a runnable state, and the scheduler will skip it, and maybe like you context switch to a scheduler, and the scheduler will context switch back to process 2. It's a little annoying, but this is how x86 does it. So they don't make this decision upfront. In a more mature full-featured operating system, you would probably say, okay, look, I can take a look whether I need to context switch in the first place. Maybe there is nothing else to run in a system, and then skip the context switch altogether if such process doesn't exist. But x86 just blindly always switches. Like as we just saw, there was no an if then else statement on this pass. It just always switches back to the scheduler. Scheduler makes a decision and maybe potentially switches back to the same process, which is wasteful, but this is how they do it. Any other questions? Okay, so if we kind of understand the gist of it, let's take a look at the switch function and specifically at how everything gets saved. I literally will talk about this again, which at this point might be a little annoying. I apologize, but then, it's kind of nice to understand how it works and like how context switch works. And in a way, you will see more of context switches in your life, especially some async runtimes implement context switch at user level between like coroutines or something like that, right? So it exists in programming languages as well, the same kind of principle, but let's understand it at least once. Okay, so we talked about the registers. We understand what these registers are. If you are more careful and you enumerate all the Coley saved registers, they will fit in this data structure. So it's like this 4 general registers: EDI, ESI, EBX, EBP, and the EAP, which is, it's not really a Coley saved register, but it's saved like every time you call a function, it's saved on a stack. And so like, let's call it a Coley saved as well, right? x86 defined a data structure, which they call a context. And the context data structure just specifically captures these 5 registers, right? And again, that's the last bit. This specifically, when you enter the switch function, only these 5 registers, and I can even make a statement that only these 4 registers are unsaved, because the instruction pointer is already saved on a stack. Because when you did a call switch, this EAP got pushed on a stack, right? So it's already saved on a kernel stack, so we can always fetch it from there. But these 4 registers are completely unsaved. And these 4 registers, we call them a context. This is the only part of the process which is not saved when we enter the switch function. And of course, inside the switch function, the very first thing we do is we're going to save those 4 registers, right? And then we essentially say, okay, got it. We probably will switch to a context of another process because it kind of represents the next process, right? Okay, let's take a look at how it works. Again, back from the beginning, which is a little like annoying, but let me repeat myself. We are running at user level. Instruction pointer points somewhere here. We have 2 stacks. The user stack is here. Currently, ESP register points to the user stack. Inside the TSS, there is a pointer to the kernel stack for this currently running process, right? Sure. At this point, this is the state of your system, GDT, page table, everything is loaded. And imagine the timer interrupt hits you, right? So essentially, saying back to the timer interrupt lecture, you have an interrupt vector, hardware picks something from the interrupt descriptor table, picks the handler, switches the privilege level. The handler is vector 32 because that's how we configured it. Remember this trap init function, which loaded the interrupt descriptor table. Essentially, we start executing vector 32. Vector 32 pushes like an error code saying, okay, the hardware didn't push the error code, so we're going to push it for them. Pushes the number for the interrupt. It's interrupt number 32. Jumps to all traps. Right now, the kernel stack looks like this, right? So the hardware saved those 5 things. Vector 32 saved these 2 things just a second ago. We are inside the all traps. We start building the trap frame. We save the segment registers, save all general registers. The stack looks like this, right? So this is like, this whole thing is our trap frame. It's on the kernel stack. Nothing else is in the kernel stack for now. Then we push the pointer to the kernel stack on the stack itself, passing it as an argument to the C function trap, right? Because it has a signature, it takes 1 pointer. So we pushed it on the stack according to the calling convention. Executing inside the trap function, did this logic of incrementing the ticks, waking everyone up. Go to this part of the trap function. We understood that we have to yield. We're entering the yield. Yield goes into the scat function. Scat function goes into the switch function. At this point, our stack looks like something like this, right? So what we're doing here, this got saved by the hardware. Vector 32 pushed these 2 fields. All traps save those fields. This thing is known as a trap frame. From inside the process data structure, there is a trap frame pointer. It points here, right? We were executing a couple of other functions. So there are some return addresses pushed on a stack. Return to all traps. Before, when we called yield, there will be instruction pointer, which returns inside the trap function. Maybe in between, we were saving some intermediate registers, like caller saved registers got saved on the stack as well. I put 3 dots here. I'm not like really specific about what goes there. Yield, then return address for the yield function. And essentially return address, like inside the scat function, our currently, since the switch function takes 2 arguments, these 2 arguments are pushed on a stack according to the calling convention, and we call this scat function. So there will be a return address back to the scat function, and we're inside the switch function right now. Make sense? These two arguments which we pushed into the switch function is a pointer to the context field of the currently running process. So this is the current process. And we say, look, we're gonna save the call state. We're gonna save the call saved registers somewhere, and we will update this context field to point to that place where we saved those registers. Call. And a second argument which we get in this function is a pointer to the context of the scheduler, meaning that, like, remember this context field. And like, if we want to switch to a scheduler, we're going to pass a pointer to the context of the scheduler. And we essentially will be able to switch to this context. Make sense? At this point, although it's not critical, x86 makes the following design choice. They say, the question is, where will you save this call saved registers? And you can say, look, I'm going to save them as a part of the process data structure. That's totally fine. That would be okay. However, they don't do it. They say the context itself will be saved on the top of the current kernel stack. So literally here in my drawing, right? Because this is the kernel stack of a currently running process. And x86, maybe it was the case how Unix version 5 did it, and x86 just followed this design choice. It's not really strictly required, but it just made this way. They say, look, the context itself will be the top of the current stack. And when we save all these call saved registers on this stack, we will update this context field to point to the top of this stack. Okay, sure, why not? And at this point, the box of this process is complete. Anytime we come back later, we have the top of the stack, we have the call is saved registers, and we have the whole stack of execution right above it, meaning that we can IRAT from here, from these 5 fields saved by the hardware, we can return to this process. So everything is saved for this process. And again, in this assumption, if the context is at the top of some kind of a stack, then means that on top of this data structure, there is a stack of this scheduler, right? So this pointer, which we passed as an argument to the switch function, is the pointer to the context data structure, but in x86, it sits on top of some stack. In our case, since this is the scheduler, it sits on top of the scheduler stack. And not surprisingly, this is the stack which we initialized during the boot sequence when we entered main. Main was executing on this stack. Main entered MP main entered schedule entered something else, and this is the stack on this CPU which we created. And each CPU will have its own scheduler stack. Make sense? Let me check a question here. And the switch function switches to the scheduler function, which switches another runnable process. That's correct. That's how it's implemented in x86. But did you get the point of this figure that we saved everything on a kernel stack of a currently running process? Even the call is saved registers, which we call the context, will be saved on this stack, and we will update the process data structure with the pointer to the top of this stack, and we will come back later to it when we switch back to this process later in future, right? And the second argument which the switch takes is the pointer to the context of the scheduler. And from this context, which sits on top of the scheduler stack, we can like essentially go back to the scheduler and run it, right? Because it's packed as a box. I mean, technically speaking, scheduler looks like a process in x86, although it's a little simplified and never has a user part. It never exits into the user land, but it has the context, right? And we passed it here. Let me change the color. We passed it as an argument to this switch function. Make sense? Any questions? Okay, so now if we understand how it works, let's see what's inside the switch function, right? As I was saying, the switch function should pack everything what is left, meaning call is saved registers, and switch to the new process. Let's take a look. So this is inside the switch function. Right now we have 2 arguments passed on a stack. We will save them in a temporary registers. Those are caller saved registers, so we're free to override them. So EAX and EDX. And after that, we immediately save all the call is saved registers by just pushing them on a stack. Because we said, okay, the context be on top of some other stack, so why not just to push them? If you decide that the context is not on the top of the stack, but it's part of the process data structure, instead of these push instructions, you will be using something like move %EBP into some address pointed by whatever the current process, right? It totally works this way as well. It doesn't have to be push. It can be a move into some data structure. It's totally fine, right? So, but note that layout of this data structure. So this is at the very top of the stack. So EDI goes here, ESI goes here, EBX goes here, and EBP goes here, meaning that the layout of the context data structure matches the order in which we save the registers. Note another thing here, that this field, instruction pointer, is never saved explicitly. Why is that? Because when we call the switch function, this call pushes the return address on the stack. And that's sufficient, right? Because when we call this switch function here, it will be a call instruction, and this return address, meaning, remember, I was drawing this EAP of the next instruction after the call instruction will get pushed on a stack, which means that, okay, sure, we can come back later we essentially can come back and start executing the instructions from this point, right? We'll see how it works, so don't worry. But at a high level, it makes sense, right? So we pushed all the call safe registers on the stack, creating this context data structure. It's on top of the currently running stack, and it's on top of the kernel stack of the currently running process. Make sense? Any questions? At this point, we're gonna switch the stacks. Meaning, as we agreed, the context is always on the top of some stack, right? Meaning that, like, if we have some kind of a stack, this is the kernel stack of the currently running process. We save the context here. And someone passed us a pointer to another context. And we're switching from this old context to a new context. This context is sitting on the top of some other stack. It's a stack of the main function, stack of the scheduler. Right? That's okay. So this pointer, we got it in the register, right? So we got it, this pointer to this stack. We got it as an argument to this function. So we will just simply load it in the ESP register and say, okay, we're gonna be executing on this stack now, because this is how we switch. So this is exactly what we're doing. So we do think two things here. So first, we will remember the current context, establish this pointer into the argument which was passed to us, right? So we got two arguments. So we got the pointer to this memory location where we're gonna save the current value of the stack, which is pointed by the ESP register, right? Let's do it first. And then we essentially say, well, we're gonna like load the ESP to start pointing to here. Let me just show you. So the first thing, save the current context, right? Remember, we got the pointer to a pointer of the currently running context, which is the old process here, as ESP +4, right? We saved it in a temporary register EAX. That's why we're saving the value of the ESP into this data structure. So specifically, what happens here, let me show you. Erase all Lincolns. Look, we got this as an argument. We got a pointer to this field. And the top of the current stack is pointed by the ESP. We're saving this value of ESP into this field with this assembly instruction here. Value of ESP is saved in a memory location pointed by the EAX. EAX points to the, it's a pointer to the pointer, right? Make sense? So we just remembered, we say, okay, we remembered the context of the currently running process. And the second instruction loads the context of a process we're switching to, which we got as an argument to this function inside ESP +8. We saved it here in the temporary register EDX, and now we're loading this pointer in the ESP, meaning that we specifically establish, maybe I have a slide here, we establish like the hardware ESP register will be pointing to this context. That's what happened, right? What we done, we simply switch the stack from one stack to another. Make sense? At this point, okay, sure, how to proceed? Remember, since we loaded this EDX into the ESP, ESP points to some kind of a stack. On top of this stack is the context. Context is crafted to match the specific layout. So we say, okay, if we pop, EDI is right here, next is ESI, next is EBX, next is EBP, next is the return address. If we pop this 4 the top of the stack will be pointed by the return address. If we execute this return instruction, we're gonna go to this return address right here, right? And so we're gonna return from this switch function to the function which called switch. Make sense? A little mysterious, no? If I ask you a question, where do we return? I will show you facepall.
Do
you
we
guys-
return?
Tell me.
Do we return to the start of the scheduler function?
Correct. Not exactly to the scheduler function, but let me show you. I never showed this code before, but you're right. So where do we return? The question is the following. How does initialization of each CPU end? And I said, okay, we're gonna inside the MP main. This is code from main. We're gonna inside the MP main. MP main calls the scheduler. And we're gonna intuitively will return back into this function. This is what's inside this function is. Scheduler itself, as I keep mentioning,
Me being a dork?
sorry, got disconnected. Why? No one knows. Okay, let me quickly finish. We're right on time. So essentially, the way we finished booting, we called this switch function for the first time. And this return address will lead us back to this line in the scheduler. So you were right. So when you were saying we're returning back to the scheduler, but to be more specific, this is exactly where we're going to return. Then we're going to finish this iteration of the loop, pick the next process to run, and again, we'll switch back from a scheduler into the process. So, and this will be the next process to run. So let me stop here. We'll come back and essentially finish it. But the idea which I was trying to push is that this return, it returns back to this scheduler. And essentially, we're going to execute the scheduler loop. The scheduler will pick the next process to run, switch into that process, and then like run the process and then back to the scheduler again. Let me take the questions, like a couple of. He got context switched. Yes. The end of the class happened. You're right. Okay, guys, thank you so much. So I will come back on Thursday and I will finish the context switch. See you.
Sorry, I have a question in that
Right.
last part.
Yeah.
So I get we return to the EIP of the stack of the new process, but if that process was also like stopped from a timer interrupt, won't we return to its scheduler,
No,
which loops?
no, we'll cover it on Thursday. But at a high level, what happens is that if that process was preempted by a timer interrupt, you enter the vector 32, all traps, trap, yield, schedule, switch. You will get back to the switch function and it will start exiting from, you're going to exit from yield, you're going to exit from traps, and eventually you're going to exit back to user level and continue running in user level. And if you were preempted by a timer interrupt and you were doing some kind of a computation, like crunching some numbers, you will continue crunching these numbers, right? Make sense?
Kind of, but isn't after like the yield, we go eventually to the scheduler, like the scheduler calls switch.
Yeah. Yield
So-
switches into the scheduler. Scheduler picks the next process to run, and maybe like 10 timer interrupts later, we're gonna switch back to the scheduler. Scheduler picks our process, which originally we looked at originally, right?
Yeah.
And it goes back and exits from a switch
But-
into the yield.
so- So I guess where I'm confused is that scheduler. So we have the interrupt, our process goes to the scheduler and calls switch, which moves us to the next process.
Mhm.
But then when we go back to that original process again,
Mhm.
we're gonna be in that process's scheduler, wouldn't we?
No, let me real quick go back to sharing and why not? So I don't know if I have this diagram, but I don't mind drawing it again. So this one, right? So if we were running in a process here, right? You see my screen?
Yeah.
Got preempted by a timer interrupt. You scheduled, you like switched here, right? To another process P2. Later, this P2 switches into the scheduler. And this scheduler will switch back. If this one was P1, it will switch back to the on this kernel stack of this process, which we saved here. Like you were running like vector 32, then yield, everything, right? But this process was running in user level. There was some kind of a user EAP pointing to some kind of instruction, right? We're gonna come back to the same stack, right? So it will be vector 32, the very top, and the yield here, and maybe switch function, right? But if we switch to the switch function, start returning on the switch function, eventually we're gonna go to user level.
Yeah, but the switch function returns to the scheduler, which is an infinite loop. I guess that's my confusion.
Okay, let's take it. I'll answer it next time. So and
Okay.
to ask the same question again, but you will get it. So it's a switch into the scheduler, switch away from a scheduler to a process, back switch to a scheduler, pick the next process, switch to the stack of that process. So you kind of you never stay on a scheduler. You always will be
Okay.
process.
Got it. Okay. Thank you.
You're welcome.